Good morning or good afternoon, and in this lecture we will be covering our structure-activity relationships for our penicillins. So before we move on to our penicillin proper, let's talk about our beta-lactam. So all our penicillins and all our cephalosporins are beta-lactam antibiotics, and they all possess this structure. So antibiotics that possess the beta-lactam ring are the dominant class of agents currently used for the chemotherapy of bacterial infections. So the beta-lactam antibiotics all carry this structure right here. Now please do take note that when we say a lactam is simply a cyclic amide. And when we refer to a beta-lactam, it specifically states it is a four-membered cyclic amide. So we will be focusing on our beta-lactam. So it is a four-membered amide ring. So let's talk about the nomenclature of penicillin. So before we discuss our structure-activity relationship, we must first know and remember how do we number and name our penicillin structure. So there are actually two ways of numbering our penicillin structure. So we have our chemical abstract system and we also have our USP system. So for our chemical abstract system, it initiates the numbering with the sulfur atom. So it starts at the sulfur atom and assigns the nitrogen at the 4 position. This is our chemical abstract. For our USP, it assigns 1 to the nitrogen atom and it will assign 4 to the sulfur atom. So you will be enlightened with the next slide. So you can see that for our chemical abstracts, 1 is sulfur, 4 is nitrogen, and for our USP, 1 is nitrogen and 4 is sulfur. For the sake of brevity, we would be using the USP method of numbering. So it starts at nitrogen and 4 is at our sulfur. Okay, so please take note of the numbering. So you start at nitrogen, then the numbering goes towards sulfur. So 2, 3, 4 is sulfur, 5, 6, and 7. That is the numbering system of our penicillin. Simplified forms of penicillin nomenclature. We have three main simplified forms. First, we have the PENAM system. So the PENAM is used for the unsubstituted bicyclic system, including the amide carbonyl, with one of the foregoing numbering systems just as described. So this is the PENAM ring. Next, we also have the more frequently seen in medical literature, which is our penicillinic acid nature, penicillinic acid. Okay, so this includes substituents in our PENAM ring. So these are now included. If we go back, those are not. Okay, hydrogen is included in the PENAM ring. However, the bimethyl substituents and the carbonyl is not. And the third form, which we will be using across this lecture, uses the trivial nomenclature to name the entire 6-carbonyl amino penicillinic acid portion of the molecule penicillin. Then it only distinguishes compounds on the basis of the R molecule of the acyl portion of the molecule. Okay, so this sort of structure right here, from here to here, can be divided into your N-acyl group, and this is your 6-amino penicillinic acid. Okay? Most of the time, there won't be any changes in the 6-aminopenicillinic acid group. There won't be any significant changes. However, most of the changes do occur in the N-acyl group, in particular to what is attached here after our acyl group. Okay, so it is similar to the figure on the bottom, in which it is divided into the 6-aminopenicillinic acid and the N-acyl group. Okay, so this is what we will be using towards our lecture. And please do take note that R is usually the one being substituted, or the other part of the structure. Okay, so for structure name and numbering, again, we start at nitrogen 1, 2, 3, 4 sulfur, 5, 6, and 7. Take note that there is a nitrogen here, then a carbonyl here, and this is your R. R could be anything, and in most of the times, it's just a carbon molecule, or it's a carbon atom. And we call that carbon atom the alpha carbon atom. So this will be used later. Again, so this is the structure. Okay, so here on the screen, you can see the different R groups that are present. Or you can see the R groups that will be presented later. Okay, so here are a continuation of our R groups. Okay, now for our parent compound, this will be our general structure. So usually when we compare activities of our antibiotics, we're going to compare it with the most basic substance. In this case, our parent compound is penicillin G, or our benzyl penicillin. Okay, so let's study the structure. Again, you can divide it here. This is your 6-aminopenicilloic acid. This is your N-acyl group. Okay, and this is your alpha carbon. Okay, why is it called benzyl penicillin? It's because you have a benzene ring attached to the alpha carbon. That is why it's called benzyl penicillin. Okay, so modifications to this structure will usually end up with different properties of our antibiotics later. Okay, so penicillin G will always come up later, and I will always try to bring it up when we're going to discuss more specific SARs. Okay, so before we move on to the next class, or the more specific classes of our penicillins, we must first talk about bacterial resistance. So there are various methods of resisting penicillin by our bacteria. However, one of the most common and the most important when designing our drugs is the property of our bacteria to produce inactivating enzymes. So the bacteria actually produce enzymes that deactivates penicillin to protect themselves. We call these enzymes that deactivate penicillin, specifically penicillinases. Okay? And among these penicillinases, there is a more specific type, which is our lactamases. The lactamases act in a way by destroying the beta-lactam ring. In essence, once you destroy the beta-lactam ring, which is responsible for the antibiotic activity, you render the antibiotic useless. Okay? So it is well known that strains of Staphylococcus aureus produce beta-lactamase. Okay, so let's take a look at our structure again. So you can see this is the beta-lactam ring. And in particular, your beta-lactamase will try to destroy the bond between the carbonyl and the nitrogen group. Okay? Once that bond is broken, it becomes penicilloic acid, which is inactive. Okay? So that's the mechanism of action of our beta-lactamase. Okay. Now, based on our recent development of producing penicillins, we have currently the ability to mass produce 6-amino penicilloic acid on a commercial scale. So this structure right here on the lower right side of the screen can be easily manufactured right now. Okay. Now, can be easily manufactured. So this structure is readily available, and all we have to do is to adjust this part of the structure right here, and we're going to attach various functional groups to our acyl amino side chains. Okay, so in essence, we always have the base compound, and we're just gonna design what other parts of the structure will be added to that point. So in general, we have our first SAR, which is the development of penicillinase resistant penicillin. So our penicillinase resistant penicillin, these are penicillin structures which are resistant to penicillinase. So examples of bacteria that uses penicillinase is our Staphylococcus aureus. So drugs that are penicillinase resistant can kill those bacteria. And the exact structure activity relationship is increasing the steric hindrance, or let's just say size for short, at the alpha carbon of the acyl group increases resistance to staphylococcal lactamase, with maximal resistance being observed with quaternary substitution. And an even more fruitful modification was that if the acyl carbon could be part of an aromatic ring structure, or even if it is a part of a heteroaromatic system. Okay, so let's take a look at the next sample. So this on the screen you can see is oxaziline. Okay, so this is our alpha carbon. If it is a part of a ring system, it actually increases its activity against staphylococcal lactamases. As you can see, there is a very large portion that is added to our penicillin structure. So substitutions at the ortho positions of the phenyl ring. So take for example, this is the alpha carbon. Substitutions at the ortho ring. Ortho positions of the phenyl ring, or the two position of a 1-naphthyl system. So this is the naphthyl substituent. You have 1. Increases the steric hindrance of the acyl group and confer more beta-lactamase resistance than showed by unsubstituted compounds. So if ever you're going to compare a structure with a naphthyl ring and a phenyl ring, if there are substitutions at 1 at naphthyl or 2 and 6 at phenyl, it is greater in terms of beta-lactamase resistance. Okay, so let's take a look at naphthalene. Okay, so this is our APA, aminopenicilloic acid. This is our N-acyl group. As usual, nothing changes there. This is our alpha carbon. And lo and behold, this is 1, this is 2 rings. This is our naphthyl ring. And you have substitutions at the second position. So the second position of a 1-naphthyl system increases steric hindrance even more and gives it more resistance to beta-lactamase. Let's take a look at methicillin. So instead here, if you compare it to the previous structure, this is a phenyl ring. So phenyl is simply this one. Benzyl. Okay. So ortho, meaning 2 and 6. 2 and 6. Also increases the steric hindrance and gives it more resistance to beta-lactamase. Next, bulkier substituents are required to confer effective beta-lactamase resistance among 5-membered heterocyclic derivatives. In particular, the members of our 4 isoxazole penicillins, our cloxaziline, oxaziline, dicloxaziline, require both the 3-aryl and the 5-methyl substitutions to have effectiveness against beta-lactamase producing Staphylococcus aureus. So this is our isoxazole on the screen. And the numbering is 3. 1, 2, 3, 4, 5. It is called 4-isoxazole. It's because the alpha carbon is at 4, or the attachment point is at 4. Okay, so it will require that 3-aryl, correct, and 5-methyl, also correct. So this is your oxaziline. Okay. The next structure is similar in nature. It's literally the same with oxaziline. However, the only difference is there is a chlorine atom at the phenyl substituent or the aryl substituent. So this is your cloxaziline. Now you might think, all our penicillin should have a bulky substituent since it is resistant to our beta-lactamase. You would think that. However, adding steric hindrance to the structure actually has some disadvantages. Okay, so the disadvantage is if you increase the bulkiness of your acyl group, it leads to penicillins that are less active than the original penicillin G or penicillin V against non-lactamase producing bacteria that are normally sensitive to penicillins. So what this means is as the bulk of the acyl group increases, resistance to penicillinase increases as well, meaning it is more resistant to beta-lactamase, but effectivity against other organisms is lessened. So that is why we call them penicillinase-resistant penicillin, or an alternative name would be our anti-staphylococcal penicillins. So these penicillins are actually indicated for staph infections. These are not indicated for anything else because they are so specialized in killing staphylococcal infections. Okay. If you're not going to treat staphylococcal infections, better move to other penicillins. So the next type is we have our extended spectrum penicillins. So another development was in the preparation of semi-synthetic derivatives was if you introduced an ionized or polar group into the alpha position of the side chain of the benzyl carbon atom of penicillin G, it confers activity to gram negative bacilli. Okay, so you actually extend the spectrum of activity of our penicillin G if you put an ionized or polar group in the alpha position. Okay, so let's take a look at the structures. Here on top, you have penicillin G, or our benzyl penicillin. This is our standard penicillin. Next, you have ampicillin. The only change with penicillin G is you added an amine group at the alpha carbon. Okay, so the amine is your ionized group. Next, you have your amoxicillin. You also add the ionized group, subgroup, or our amine, and you also add a hydroxide on the benzyl substituent. Okay, so these are our two samples of extended spectrum penicillins, our amoxicillin and our ampicillin. Please take note of the differences in the structure. So Pen-G is the basic. You add an amine group at alpha carbon, it becomes ampicillin. You add an amine group at the alpha carbon and an OH group at our benzyl substituent, it becomes amoxicillin. Another example of our extended spectrum penicillin is our carbenicillin. So here, there is an incorporation of an acidic substituent at the alpha benzyl carbon of penicillin G, and also imparts a clinical effectiveness against gram-negative bacilli. Therefore, it extends the spectrum of activity to include organisms that are resistant to ampicillin. So you have our Pen-G. You have carbenicillin on the bottom. So if it is ampicillin, this is ampi. Instead of NH, you added a whole carboxylic acid. Okay. So this is our carbenicillin. It has roughly the same activity as our ampicillin. However, it has a broader range against gram-negative bacteria, including our Pseudomonas, Klebsiella, Enterobacter, Proteus, Serratia, and Providentia. However, please do take note that the potency of carbenicillin against most species of penicillin G sensitive bacteria is lower than either Pen-G or Pen-V, because probably because of poorer penetration of a more highly ionized molecule into this bacteria. So in essence, is carbenicillin is good against gram-negative but less effective against gram-positive. And carbenicillin is active against both beta-lactamase producing and non-beta-lactamase producing strains of gram-negative bacteria. Next, we have our uredopenicillins. Our acyl-uredo substituted penicillins, which are represented by aslocillin, meslocillin, and piperacillin, exhibit greater activity against certain gram-negative bacilli than carbenicillin. Although our acyl-uredopenicillins are acylated derivatives of penicillin, the antibacterial spectrum is closer to carbenicillin. So our uredopenicillins are more structured towards gram-negative bacteria. So you have Pen-G on top. Sorry, it's ampi. You have ampicillin on top, and you have your aslocillin on the bottom. So this is the changes applied to our ampicillin. And you have piperacillin. Among these drugs, the most common ones you will encounter is piperacillin. Okay. More SARs is in terms of protein binding. So the nature of our acyl amino side chain also determines the extent to which penicillins are plasma protein bound. Penicillins with low polar or ionized substituents in the side chain exhibits low to intermediate fractions of protein binding. Those with non-polar lipophilic substituents are more than 90% protein bound. So, summary, as substituent ionization goes up, it becomes less protein bound. As lipophilicity goes up, it becomes more protein bound. Okay? The more lipid soluble it is, the more protein bound it is. The more ionized it is, the less protein bound it is. And finally, we have our final SAR is our allergy to penicillins. So allergic reactions to various penicillins ranges in severity. So it could be a simple rash to anaphylaxis. Sensitivity to penicillin is very common, and you should always ask the patient if they have any allergies to penicillins before you administer one. Okay, so it is present in all commercially available penicillins, may it be general Pen-G, uridopenicillins, cephalosporins, or more specific penicillins. Okay, so it is assumed that it is based on the beta-lactam structure, since our 6-acyl-aminopenicillinic acid also demonstrate sensitivity to penicillins. So the 6-acyl-aminopenicillinic acid comes from our cephalosporins. So even though, so let me draw the structure of penicillin. So penicillin will look like this one. And our cephalosporins will look like this one. It's roughly the same. Okay. So it's actually a theory that this whole structure is what causes our penicillin sensitivity. Please do take note that penicillin sensitivity is across all penicillins. So if you are already allergic to penicillin, you are not to be administered other types of penicillin, including our cephalosporins. Okay, so most of the time, if you are allergic to penicillin, you're going to be administered a different class of drugs, usually our macrolides like erythromycin, our azithromycin, and our I forgot. It starts with the letter C. Okay. So anyway, that is the conclusion of our SARs. The lecture would also be uploaded separately. So please take note. You should read your book along with the lecture materials. That would be all. Thank you for listening.